Watch a modern industrial robot welding metal or sorting parts at high speeds. But if we strip away the steel casing and the factory floor, we are left with an electromechanical manipulator operating purely within three-dimensional spatial coordinates. What remains is the machine's kinematic architecture, the specific physical arrangement of mechanical joints that dictates what the hardware is capable of doing. Before a robot can take on an industrial role, its potential is first determined by this underlying geometric design. To achieve arbitrary positioning and orientation in space, a system requires exactly 6 degrees of freedom, 3 axes of linear translation, and 3 of rotation. If we focus strictly on the first 3, we see how translation establishes a robot's fundamental geometry. These 3 axes define the workspace, the absolute physical boundary that the robot's end effector is mechanically capable of reaching. By combining Prismatic and Revolute joints, we can build the 5 core kinematic architectures to see how they uniquely shape this workspace volume. These 5 configurations provide the structural framework for almost every industrial manipulator in use today. Every industrial arm is built from 2 primitive blocks, the Prismatic joint and the Revolute joint. The Prismatic joint provides purely linear, sliding motion along a single axis. The Revolute joint operates by rotating around a central axis. A Cartesian coordinate robot uses exactly 3 prismatic joints mapped to the X, Y, and Z axes. As the robot moves, its end effector outlines a rectangular workspace, forming a rigid, predictable bounding box. This configuration provides high structural rigidity and a significant payload capacity because it relies entirely on linear mechanics. This makes Cartesian robots the standard choice for gantry cranes and heavy material handling, where raw stability outweighs the need for complex, angled movement. If we swap the base linear slide for a Revolute joint, we create the cylindrical robot. The end effector now traces a circular sweep, creating a much larger volume of reach from a fixed center. By combining vertical, radial, and rotational reach, this geometry is specialized for loading and unloading parts around circular machines. Replacing the vertical slide with a pivoting pitch joint results in a spherical robot. Here, the workspace transforms from a cylinder into a hemispherical arc. This spherical configuration provided the mechanical basis for the first machines to ever enter a factory floor. The UNIMATE, the world's first industrial robot, was built on this exact spherical architecture. Its reach allowed it to extract hot metal from die casting machines, a task that required extending deep into hazardous environments from a stationary, rotating base. By introducing rotational joints, the robot's swept volume shifts from rigid boxes to sweeping arcs, expanding its operational versatility. The articulated robot abandons linear tracks entirely, using exclusively Revolute joints for its base, shoulder, and elbow. This configuration is anthropomorphic, directly following the skeletal geometry of a human arm. This design provides dexterity, the mechanical ability to reach over or under obstacles by bending at the elbow, a movement Cartesian robots cannot duplicate. However, this dexterity comes at the cost of the structural rigidity found in linear models, requiring more complex engineering to maintain precision. These robots are primarily used for the complex, continuous paths required in automotive welding and painting. By prioritizing spatial flexibility over absolute rigidity, the articulated robot has become the most common tool in modern industry. There is a specialized variation of the articulated arm called the SCARA robot, designed for a narrow set of precision tasks. Its layout consists of 2 Revolute joints that rotate strictly in the horizontal plane, terminating in a vertical prismatic joint. This creates selective compliance. If force is applied sideways, the arm flexes slightly, but when force is applied straight down, the machine remains completely rigid. The SCARA is unyielding in the vertical z-axis, but compliant in the horizontal plane. This allows it to perform high-speed electronic assembly, where pins must be driven straight down into circuit boards with high force, but 0 horizontal deviation. By utilizing this selective rigidity, the SCARA layout maintains the vertical force necessary for delicate insertions, while protecting the components from misalignment. While the first 3 joints of these architectures define a robot's XYZ position, full manipulation requires 3 more degrees of freedom. These final 3 joints, the wrist, provide the roll, pitch, and yaw necessary to orient a tool or part at any angle. All 5 models are serial architectures, meaning links are stacked sequentially in an open loop. In this chain, structural errors and vibrations compound. A single millimeter deviation at the base translates into a much larger error at the end effector. This is why some high-precision tasks use closed-loop parallel robots, which anchor multiple links to a single platform to maximize rigidity at the expense of reach. Industrial robotics remains a fundamental trade-off between the expansive reach of a serial arm and the structural stiffness of a parallel system. In specialized research labs, the traditional reliance on discrete, rigid joints is being phased out. Continuum robots are being developed for micro-robotic and medical applications where rigid metal hinges are too cumbersome. These machines use pneumatic artificial muscles to create hyper-redundant movement, allowing a catheter to bend seamlessly around the internal structures of the body. As robotics moves from factory floors into the human body, the rigid spatial models of the past are giving way to continuum mechanics.